I'd like to present some data from the Explorer 45 satellite that seems to be directly relevant to the hot ring current plasma interaction with the cold plasmaspheric plasma. These data are from S-cubed, or Explorer 45. It was launched on the 15th of November 1971 into an orbit having a 5.24 Earth radius apogee, a 220 kilometer perigee, an inclination of about 3 degrees south, and an orbital period of 7.8 hours. The fact that we're only 3 degrees from the geographic equator means that we're always less than 15 degrees from the geomagnetic equator. Complete pitch angle distributions were obtained by sectoring the satellite spin into 32 pieces. So we have 32 samples in 360 degrees. The pitch angle distributions, therefore, are a reasonable approximation to the equatorial pitch angle distribution. The energy range from 1 kilovolt to 800 kilovolts for protons was covered in 28 steps. From 1 kilovolt to 560 kilovolts was covered in 20 steps for electrons, and today we're going to concentrate only on the protons. The orbit is shown on the board. On its outbound pass, the satellite crosses the dusk terminator at about an altitude of 3.5 Earth radii. As it does on its inbound midnight pass, apogee is at 2100 hours local time. In the first slide, is the pointer here? There it is. We show the magnetic activity of the period of interest. This is December 1971. There are two sudden commencements occurring on the 16th and on the 17th. 5 high-latitude magnetograms are shown just to show what substorm activity looked like at this time. Explorer 45 orbit coverage is shown in this particular bar graph. We'll show data from orbit 97, which is a pre-storm quiet. We'll concentrate on orbit 103, which is a recovery phase orbit, and for completeness, we'll indicate some main phase data from orbit 101. I don't at all understand the injection process. I think we understand the recovery phase, so we're going to emphasize recovery phase effects. That is, after the ring current became symmetric. This is now orbit 102. It's a different recovery phase orbit. This is at an L value of 5.4 Earth radii. We've started the rounding distribution at the higher energies. The lower energies are still flat, and you'll see that the samples that are taken right at the very smallest pitch angles we measure show drops that range anywhere from factors of 2 to 5. Now, the fact that our angular aperture plus the angular scan during our pitch angle scan is significantly larger than the loss cone, the fact that we see a drop is clearly indicative of a very empty loss cone in this flat top type of a distribution. We are left then with looking at data of this type, and I want to repeat, I guess, one thing. Every recovery phase orbit, from orbit 102 through orbit 111, when we got back to pre-storm values and the plasma pause was never exited by the satellite, every recovery phase orbit shows this basic pattern in its overall transformation from the flat to rounded distribution, as well as the empty loss cone when the pitch angle scan is sufficient to see it. So we do have 2 experimental observational facts during recovery phase in this storm. That is that we do see a transformation from a flat top to a rounded pitch angle distribution that has an altitude dependence such that the transformation takes place at higher altitudes for higher energies. The second one is in the region of the flat top distribution. There seems to be an empty loss cone. All the data we've seen are from the inbound orbit of S-cubed. During recovery phase, the outbound dusk orbits show the same pattern. One thing that I didn't mention in the previous slide, and that is that if you go to a given altitude and look at the energy dependence of the evolution of the pitch angle distribution, you find that as you go to higher energies, the width of the flat top becomes narrower. The conclusion we come to, based simply on these experimental facts, is that outside the region of the rounded pitch angle distribution, the symmetric ring current recovery phase is about a perfectly stably trapped particle population as you want to find in the magnetosphere. There is 0 or negligible loss due to pitch angle scattering, and that as this particle population is traced to lower altitudes, you enter a region of weak to moderate pitch angle diffusion, which is exemplified by the rounded distributions. The reason why we categorize it as weak to moderate is, first of all, the loss cone is not full as you come down to lower altitudes. And secondly, if you stay within a given region of space and have a flat distribution on one orbit, when you come back around on the other orbit, that will have transformed into a rounded distribution, so that gives us a time scale of less than 7.8 hours to go from flat top to rounded. So it's a weak to moderate pitch angle diffusion process that seems to be excited. We've tried to summarize this in a schematic model of the recovery phase, where as you go out in Earth radii, in the inner regions you have a fairly stable plasmasphere. You have a plasma pause region because each particle picks the appropriate value of b squared over n at which to start diffusing. And the S-cubed observations indicate that there's a region just above the plasma pause region where the ring current plasma is stable. It transforms into a moderate diffusive mode unstable to ion cyclotron generation in this region of the plasma pause. High altitudes transforming at the high energies transforming at the high altitude edge, low energies at the low. A resonant energy equation based on the S-cube data is shown here, and by inference with low altitude measurements above the Explorer 45 apogee, which is 5.2 Earth radii, there may very well be a strong diffusion region called the plasma sheet, which has an unknown wave mode producing the instability, where you would observe an isotropic pitch angle distribution. The low altitude observations can be placed consistently into this picture by simply allowing for field line expansion during the storm. Thank you.
Thank you, Rick. Well, that was classic Don Williams. Those of you who knew him know him. He was one of the pioneers of radiation belt physics, obviously. As you can tell from his talk, he worked his entire career studying electrons and ions and pitch angle diffusion and particle loss and diffusion processes in the magnetosphere. Had a very long and distinguished career. And that was classic Don. I want to cover several things about his career today, and I'm glad to have the opportunity to do that. I'm the TBD in your program because I never got back to Rick sufficient time to have my name included. It's been a terrific conference. I'm awfully glad to have the opportunity to be here. I've only been at a couple of these others previous Yosemite conferences, but they were always very good as well. So Don had his bachelor's degree in physics at Yale. He spent 2 years with the Air Force. Then he got his master's and PhD physics at Yale, and he went through his career, as you can see here, and I'm going to highlight one or two items from each of these. Obviously, he just spoke about, no, I'm ahead of myself. When he was at Hopkins Applied Physics Lab, he was involved with the particle detector on the spacecraft 1963-38C. Those of you who are old enough remember that. It was a very famous spacecraft, had a tremendous amount of publications resulting from it in studying of the electrons at low Earth altitude, 1,100 kilometers, circular orbit, polar orbit spacecraft. In fact, one of the most important things that came out of that was the Williams and Meade model, magnetospheric model, using the electron data only at 1,100 kilometers. They published this in JGR in 1965, where they first Gil Meade put in the neutral sheet current, stretching the magnetic field. And this model was really a model that had been used, that was used for years afterwards, and modifications there too. I collaborated with Don in a paper in 1968 where we used data from a 1963-38C at 1,100 kilometers and Explorer 26. Bell Labs had particle detectors on Explorer 26 at higher altitudes near equator. And we compared electrons, trapped electrons at low and high altitudes. At that time was not known in terms of diffusion processes in the magnetic field and all along the magnetic field lines. Don went on then to Goddard, as shown here in 65 to 70, and he got involved with the S-cube program, and you just heard his discussion of the ion measurements on S-cube, and which was called Explorer 45. There were I don't think there were any other S-cube programs after Explorer 45. The intent at that time was to have a uniform spacecraft bus, and you could put all kinds of instrumentation on a uniform bus, but it never went very far. One of the important things that came out of his activities at Goddard also was his conference on magnetospheric physics in 1968 in the State Department auditorium. There were a few of us here that were probably at this meeting. I'm not sure. Dick, were you at this meeting? You were there. It was a very important conference in the context of magnetospheric physics. It's probably the first one that was really magnetospheric physics oriented. The United States was dominating the program at the time. And at that conference, there were 3 Russian scientists were there. First time the Russians had come to the United States to talk about magnetospheric physics and talk about the space program. There were Gringaus, who had low energy measurements on Soviet spacecraft, to measuring the plasma pause. You remember that, Don. You were at this conference too, I'm sure. Indeed, indeed. Bob Helliwell, all the luminaries of the field, including the discoverer of the plasma pause here, Don, was at this meeting, and you probably have a paper in there if I'm not mistaken. Also at the meeting was Vernoff. Vernoff was responsible for the high energy energetic particles on the Soviet spacecraft at the time. And the third Soviet attendee was a chap named Zhulin. Zhulin was nominally a space plasma physicist, but all of us at the conference and subsequent to that recognized that he probably was the keeper and the minder and the Soviet minder of the Soviet scientists in attendance. It was a very, very important conference. It was organized basically by Don, Gil Meade, and some others at Goddard. I don't remember who all the organizers were. I'm sure that Axford has a paper in here, Alex Dessler, and others of the luminary from our field at that time. And Gil Meade was involved as well, importantly. And I want to comment a little bit about Gil Meade because he was an important collaborator with Don, and Gil was a really important theorist in our field early on, and he has a very interesting background. In fact, the obituary for him in the Washington Post reads, Gilbert Meade, a retired NASA physicist and an heir to a paper manufacturing fortune who emerged in the 1990s as one of the most prolific arts philanthropists in Washington, died May 29, 2007. Meade lived in relative anonymity and frugality for decades. Gil Meade was the one who did this model, Williams and Meade model, and he was at Goddard, and his wife was there as well. They were very influential in space physics, but Gil was the heir of a paper fortune in Wisconsin, Consolidated Papers, and by the time of his death, or his wife's death, J. Lee Meade died in 2012, they had donated of the order of $50 million or more to arts in the Washington area, particularly theater arts. And there are several installations in Washington named for the Meades, and there's a Meade Foundation now that follows on that, plus aid to children. Gil was quite a guy, and he was quite a theorist at Goddard. He retired 1989, I believe. He spent 2 years, earned a law degree at the University of Maryland, and did some legal work all pro bono for friends and colleagues who needed legal work, but spent most of his time doing philanthropy after about 1991, 92 or so, and was an important collaborator with Don, as I indicated here, for more than a decade. Don then went to NOAA SEC, the Space Environment Center, which is now the Space Weather Prediction Center, where he was involved very much with the IC mission. He was involved with the Energetic Electrons and Ions instrument on IC-1. He was also a collaborator on IC-2 with Kepler. That was called a mother-daughter mission, not a father-son. It was mother-daughter. The mother spacecraft was IC-1, and the daughter spacecraft was IC-2, and he was a collaborator on that. And as at NOAA SEC, but then mostly at Johns Hopkins, he was in the PI on Energetic Electrons and Ions instrument on the Galileo orbiter spacecraft. And those of you with Galileo, like Margie, of course, recognize Don's activities there on Galileo. Finally, at the end of his career in 1990, 1996, he became the director of the Research Center at the Applied Physics Laboratory. This is a picture of Don in 1996. He hasn't changed very much from the video that you just saw. And here's a picture of Don in August 2012 at the Van Allen probe's launch party at Kennedy Space Center. He's moved to Florida, and he came to the launch party, and this is Don with me. And if you look at Don is nearly 80 in that picture. That says something. Those of us who do magnetospheric physics stay young all of our life. Thank you very much.